This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
So next presentation will be delivered by Pasqal, and it's my pleasure to welcome Dr. Heejeong Jeong, who is head of quantum computing at Pasqal, Korea. So she will be telling us about quantum computing work at Pasqal.
Hey, can you hear me? Hello, everyone. It's really nice to be here, to meet an old friend and a new friend, and then have a wonderful dinner that I realized finally my name represents single atom trapped in an optical tweezer, fluorescing a light. Okay, just this morning. Okay, so I'll talk, so my background is experimental AMO physicist. So, but I know some of you are having a similar background, so I think I'll talk about Pasqal neutral atom QPUs toward quantum reality. Okay, Pasqal is a unique mix of science and engineering, and our mission is to engineer neutral atom QPU and make them reliable, stable, and industry grade. We come from a scientific excellence, so that our co-founder and is this? Okay, working. Co-founder and Nobel Prize winner 2 years ago, Professor Alan Aspect would like to say, when there are no fundamental limitations, engineers find a path. So all the fundamental discoveries have been made in neutral atoms for last decades, and to control, to entangle, and manipulate single atom. So we are now moving into the engineering phase. So since established 2019, with 5 employees, Pasqal has grown up. And then now, it's all around the world, we have almost 300 employees. So as a global company, Pasqal has its headquarters in Paris, and has subsidiaries in Canada, South Korea, US, and Saudi Arabia. And we have more than 40 clients and partners, and we already achieved more than 1,000 single atom array for qubits toward 10K qubit number of qubits. And we have applied 55 more patents and applications. And I'm based in South Korea, and one of the subsidiaries that covers Asia Pacific regional activities. Okay, so how do we went from a laboratory experiment to integrated product ecosystem? So our flagship products are hardware products, the Orion generation of processors. What you see here is our first generation of the processors, Orion Alpha device. This industry-grade device is plugged into Microsoft Azure Quantum Cloud, and it is and can implement use cases of our clients and partners. So this shows the building blocks. This schematic shows the building blocks of our technology. So our qubits are odd atoms that we can control with light. So everything happens in the vacuum chamber that has low pressure. You may feel at the pressure that you may feel at the surface of the moon. And we individually control and trap and control atom with tightly focused beam, laser beam. So that technology has been developed over the past decades, and to encode quantum information on our atoms, we use additional laser lights. So our zeros and ones correspond to the distinct electronic levels of atoms, so that we can we can make a transition between those states using laser light. For the readout, we use standard camera like EMCCD to distinguish zeros and ones at the end of the computation. So neutral atom quantum processing units are very powerful in a sense that we can implement various computing paradigms. You can use it for analog quantum computing and digital quantum computing. In analog mode, we continuously tuning the system Hamiltonian in time, and it is really powerful, and it already demonstrated the result beyond classical supercomputing capabilities. As you see on the right side, for the quantum material simulation. Of course, we can use digital gate-based digital mode in the future, and in that mode, the algorithms are broken down into a sequence of gates that modify the system. But interesting thing is if we think about what we need to calculate those analog mode experiments on the digital gate. We actually need a very large number of gates with excellent fidelity, which is typically 10 to the 6 number of gates with infidelity below 10 to the minus 6 to keep the 1% of error as in the analog mode. So neutral atom QPU gained a lot of momentum recent years. And here are two figures of merit that assess various platforms with each other toward fault-tolerant quantum computing with quantum error correction. The left-hand side shows gate error rate, which should be below 10 to the minus 3 threshold. Of course, ion trap were the first to achieve below 10 to the minus 3 threshold, and superconducting type caught up and managed it at the level of ion trap. As you see here in the neutral atom, it started much later, around 2010, and its gate error rate rapidly drops toward the threshold. When it comes to the number of gates, neutral atoms are clearly in the lead, as you can see. So, and then advancing toward 1,000 qubits. So, for example, only this year, Pasqal headquarter R&D team demonstrated more than 1,000 atom traps in a single shot, as you can see at the center. After the rearrangement, it forms deterministic 828 atom array qubit registers. This is important for the scaling QPU. So far I've talked about technology, and then what makes Pasqal specific based on our approach? Our approach is strongly focusing on engineering, because we need higher stability, uptime, and repeatability so that practitioners can use them. We've been improving modular design submodules with well-defined interfaces at the hardware level, and it's beneficial and provide stability, ease of maintenance. And we've been continuously improving the capability of our device while keeping interface fixed. So here I show you two examples of the subsystems that is developed inside Pasqal and for the various features of QPU. That is the key attaining high uptime so that our Orion Alpha device is connected to Azure cloud service. It's operational 90% of the time, 24 hours, 7 days without human intervention when it's put in the production mode. If you think, I mean, it is remarkable if you think about how it is difficult to make something that is operating a few % of time in the lab and make it industry product that is 90% of the time available to use it commercially. So as a sign of stability of our Orion Alpha device, I can show you a few examples of use case that implemented by our clients and users. It ranged from various fields and domains, such as biochemistry, telecommunication network, finance, and mission planning for satellite. So all the algorithms are fallen into 4 categories, such as graph machine learning, optimization, quantum material, and solving partial differential equations. Okay. So we've achieved remarkable progress with major players in the global industry, recognizing the momentum at Pasqal. For example, we signed on on contract with Saudi Aramco this May to deploy 200 qubit in qubit device in Saudi Arabia. This is a significant milestone, as it is the first QPU acquired by a private company that is commercially owned. And then we also deployed 2 Orion Beta devices to 2 HPC centers in Europe, one in France and one in Germany. This 100 qubit QPU will be connected to their classical supercomputing resources. So we need to orchestrate workflow between classical and quantum devices. For that endeavor, we are partnering with IBM to define interfaces and standard way to integrate between quantum and classical device for quantum-centric supercomputing. So what comes next then? To boost the performance of our QPU, we are working on qubit scaling, addressability, and repetition rate. And we also work on error-corrected quantum computing, such as error correction and gate operation and interconnect. And we also work on the software so that ultimately we would like to increase the usage and QPU hours for our clients and partners to use it. So we've been improving, implementing collaborative platform so that our clients and partners to learn it, use it, and understand the algorithm by an open source software stack. So for example, Pulsar is our high-level library for digital and analog software platform. And we also provide Pulsar as a low-level library to design and design atomic array and then simulate pulse sequences at the fine-tuned machine level. So finally, I'll show you our roadmap, focusing on both technology and product. So such as maximum number of qubits and addressability and repetition rate. For the quantum processors, Orion Alpha device is already in the service in Azure Quantum Cloud. And we deployed Orion Beta to 2 HPC centers. And then Orion Gamma device will be deployed in Saudi Arabia by the end of next year. Okay, so also we have Pasqal delegation at QTML this year. So if you have any question, you can come to us. Please come to us. And Casper will have a talk tomorrow. And then Annie and Vitatus had a poster yesterday, but you can talk to them. And okay, with that, thank you very much. Yeah, thank you.